Hello again, here Mr. Sorrentino here, going over things from your notes here. And now in this video we're going to talk about 1.3, linear functions, slope, and applications. So here we're getting into slope, which is something we use to describe lines and write the equations of lines. So we're moving towards dealing with that. And slope is a concept that, again, students often confuse different parts of it, confuse coordinates. So let's go over some of the definitions of it. Um, First of all, it's given the symbol m. Not exactly sure as to why. I'm sure there's some kind of historical reason for it, but for whatever the case is. One way it's defined as rise over run, which is basically a vertical change over a horizontal change, or a change in y over a change in x. And that change is often represented in different ways. You know, you might see delta y over delta x. But these two are, formulas for the slope. Basically, if I'm given 2 points, x1, y1, and x2, y2, where again, these two things could be interchanged quite easily. It doesn't matter which one you're naming x2, y2, which one you're naming x1, y1. If I carry through the subtraction of the y coordinates on top, because remember the y's are on top, y's rhymes with rise, and I subtract the x's on the bottom in the same order, which means whichever y coordinate I took first, in my subtraction on top, from the same ordered pair, I take the x first on the bottom. And that's going to help me calculate my slope. So it's a pretty simple formula. It's just one that a lot of students will often confuse. Now, there's different ways to find slopes. So let's have a look at different ways it could be represented and asked of you, and so you know how to do it. Now, for part A of example 1, you're asked to find the slope. Now, you have a lot of these good dots right here that are given to you pretty outright, so you could easily define or distances between them. And so I could look at it and say, well, if I go from, say, for these two consecutive points, here I'm going up 2 and I'm moving right 1, I could say that based off of that, m equals 2 over 1 or 2. But I could have done that with even bigger points to say, okay, well, what if I went from this point here to this point here? So okay, well, I go up from here to here. That was up 6. Here I'm going right 3. Remember, up and right are positive directions, down and left are negative directions. And so from that I would have said that m equals 6 over 3, again rise over run, but again that's still 2 as well. So they both agree to each other, so it doesn't matter which points of reference you use, as long as they're on the same line, you're good. Just make sure you simplify your fractions a little bit. If you're given nothing but coordinates, though, yeah, you could graph it and then count them and things like that, and count spaces like I did for the part A. But again, I just have to use the formula for this. So m, and again, it doesn't matter which one I take to be x1, y1, x2, y2. I want to take the two y coordinates and subtract them. So I'm just going to start with the 7 first, minus a negative 5. Since I started with this point's y coordinate first, I'm going to start with its x coordinate first on the bottom. So I'm going to have negative 1 minus 3. 7 minus negative 5 is the same thing as 7 plus 5, so that's 12. Negative 1 minus 3 is a negative 4, and that becomes a negative 3. So the slope for that line is negative 3. And in a very similar fashion, this is using more of a function notation, but what it's telling me essentially in these cases is that, this means that I have a point at 0, 4 is a coordinate, because remember, this is saying, okay, when x is 0, the function value, or y, because we always assume that y equals f of x, is 4. So when x is 0, y is 4. When x is 3, y is negative 2. And they do have a couple problems out of your textbook that present it this way. And so if I want to figure out the slope for this, again, it doesn't matter which order I take them. I'm going to take the 4 first for the y, minus a negative 2. Since I took the 4 first from this point, I got to take the x coordinate from that point first on the bottom. And so now I'm going to have a positive 6 over a negative 3, which equals a negative 2. So slopes are pretty simple to calculate as long as you know what you're looking for and that you're keeping your variables straight. Now, slopes are a characteristic of linear functions. And so basically, if you could establish that there is a slope, a constant slope, that means that you have a linear function. So when you look to example 2, you're asked to determine whether or not the table shows a linear function. Now, there's different ways to complicate this, but one of the things that they tend to do most of the time in your textbook, and this is like this, is they're pretty nice and they'll say, okay, well, if you look here, as you go from x value to x value, each time here, let's get a pen on here, I'm going plus 1, plus 1, plus 1. They don't have to always do that. Now, if the y's, since the x's are going up by 1 each time, as long as the y's are changing the same as I go from y value to y value, that would indicate that I have a constant rise over a run. So when I look at if I look at this side, that's a minus 3. That's a minus 3. That's a minus 3. And that's a minus 3, which that indicates that I do have a constant slope of negative 3 running between these points. So this is a linear function. How about the next one? Is the next one a linear function? Well, it's a very similar instance here. Each one of these are going up by 1 as I move from x value to x value. So if I have a constant change between the y values, that would mean the same thing. So here, I'm increasing by 2. Here, I'm increasing by 2. Here, I'm increasing by 3. Here, I'm increasing by 3. So I see two different slopes being presented in this particular plot. And if I would plot these points, I would see that it would look like it's bending if I was like tracing the line through them. So this one is not a linear function. So what you're looking for when you're just trying to establish something's a linear function. Now, if you have a picture in front of you, it's going to be kind of obvious because you could be. If you only have 2 points, it will be a linear function. If you have 3 or more points and they're not all lining up along the same linear path, obviously it's not linear. And certainly, if you're giving ordered pairs like this, you can plot them and determine that. But you just look to see if there's a measurable slope between the points and it remains constant. If it does, then you're good. Now we get into a particular format for the equation of a line. Now, up to this point, most of our graphing has been just, picking some x values, calculating out the y values, plotting. If it's a linear function, it can be put into this format, which we call the slope-intercept form, y equals mx plus b. This is the format that's most often used because it's the one that actually, that your calculator would make the best use of, because this is also in a function notation, because if you replace y with f of x, same thing. Now, the y, the x, the plus, the equals are all part of the structure of this. They would always be present. The plus sign might change depending on what the value of b is. M and b are constants. They're going to be replaced by numbers in each one of these formulas. So the number that's attached to the x is going to tell you the slope. The number being added to the x term is going to be your y-intercept. So when we look at this, graphing this, if I have it in slope-intercept form, it's pretty easy. So let's look at this first example here. Zoom out a little bit. When I look at this this is in the right format. The only thing that's different is instead of saying f of x, we're just saying that y equals something. But don't let that throw you. Remember, y is the same thing as f of x. Y equals 2x plus 1. Same thing. That means that the slope is 2. And it's often better to think of it as a fraction. It's 2 over 1, which means we go up to right 1. Now, that doesn't help me yet because I haven't figured out a point to start at. I had to figure out one point on the line, and then I could use that slope to find the other ones. Well, that's where this one comes in. That means that b equals 1, and this is the y-intercept. Now, y-intercepts means they cross the y-axis. And if they cross the y-axis, they have to have an x-coordinate of 0. So basically, 0, 1 is a coordinate on this graph. So 0, 1 is a point on this line, and then from there I can plot other points. So I can say, okay, well, if I go up to right 1, up to right 1, up to right 1, up to right 1, I can also realize that because of negatives, negative 2 over negative 1 is also equal to 2. So, and that would tell me to go down to left 1, down to left 1. Since I usually don't use a ruler for this, I like having all the points that I could possibly have, so I could just graph the line like so. So pretty straightforward. In the next example, B, the issue is we don't have this in slope-intercept form. This is what we would call a standard form. Sometimes it's called expanded form. This form of a linear equation is good for solving systems of equations, which is something we're going to get more into all the way in chapter 6. But for graphing purposes, there's ways of graphing this, but one of the ways that we could graph this is simply converting this into slope-intercept. I want to make this slope-intercept. And essentially, to turn any linear equation into a linear equation in slope-intercept form, there's only two things I would have to do. Solve for y, and simplify. That means if there be any like parentheses that would be a part of this, which will happen more so when we talk about point slope form. I would work those out. Any cancellations or fraction simplifications that could be done, I certainly should do those as well. So if I take the 3x plus 4y equals 12, and I would subtract 4x from both sides, or 3x from both sides, in order to start getting the y alone. I would then divide both sides by 4. Maybe show a different color here. I have to remember, though, that essentially I am dividing this entire quantity by 4. And since it has two terms, both terms need to be divided by that 4. So y is going to be negative 3/4 x plus 3. And now that's in slope-intercept form, which means that when I look at this, the slope is a negative 3/4, which you can count as either a negative 3 over 4 or a 3 over negative 4. Depending on like how much room you have and where you're plotting things, I mean, one might be more beneficial than the other, or you may use both in order to get as many points as possible. Because this one here means down 3, right 4, whereas this one here means up 3, left 4. They move in the same general direction as a result, and then you would see things line up. that slope doesn't mean anything to me until I'm able to, um, figure out a point that this thing passes through. And so I know that the b value is 3, which is telling me the y-intercept. And since, again, the y-intercept has to cross the y-axis, and anything on the y-axis has an x-coordinate of 0, that means that this point is 0, 3. So 0, 3 is a point on this line. The rest of them are done by doing a negative 3, 4 slope. So either down 3, right 4, down 3, right 4, or you go up 3, left 4, up 3, and left 4. And this time I'll pull out the ruler on this one. There we go. And there would be my line. So if I have something that's not in slope-intercept form, I can certainly convert it to slope-intercept form, and that would work wonders for that. Now what we need to do is look at two special types of lines, because anything that's written in slope-intercept form, and I can clearly see the y equals mx plus b format, those lines are going to be slanted. Sometimes we refer to them as being oblique, although oblique can mean many other different things as well. But there's two other types of lines we have to keep in mind, and we want to be able to see what those look like and see what their equations look like. So let's see what they look like. Now, one example would be the equation of something like y equals 2, or y equals any number. What this is indicating is that the y-coordinate is always 2 despite the value of x. So that means that x doesn't matter to this. X has no bearing on what the y value is. Y will stay 2 no matter what x is. So if x is 1, y is 2. If x is 2, y is 2. If x is 3, y is 2. If x is negative 1.5, y is 2. So no matter what x would be, no matter what x value it would take on, the y value would always be 2. And so basically, this would be the line. So this is a horizontal line. If I pick 2 points on this line to figure out what its slope is, here's 1, 2, here's 3, 2. I'm going to use the slope formula, but I could probably do it just by counting and things like that. But for the sake of argument, I subtract my y's, I'm going to have 2 minus 2. I subtract my x's, I'm going to have, we'll say just 3 minus 1. Which gives me 0 over 2. And 0 divided by anything except 0, but 0 divided by any other number is just 0. So the slope of this line is 0. So when I have an equation that says y equals a number, it's going to be a horizontal line, and the slope of a horizontal line is 0. What about a vertical line? Now, it doesn't take someone to be a genius for this one. If y equals a number is a horizontal line, then it kind of stands to reason that x equals just some number is a vertical one. And the reason why it works that way is because this is saying that the x-coordinate is always negative 3. Since y is not appearing in this formula, y doesn't matter. So y could be anything, x will always be negative 3. So, x could be negative 3, y could be 1. Or it could be 3, or it could be negative 4, or it could be negative pi, which would be something like right here. So basically, x equaling negative 3 would be this line right here. And it's vertical. Now, if I just pick some random points on this, say I'm going to have negative 3, negative 2, and negative 3, 1. Those would be points on this line. And I tried to calculate the slope from those. Well, I'm going to have negative 2 minus 1 on top. I'm going to have -3 minus -3 on the bottom, which gives me a -3 over 0. We talked about numbers having zeros in the denominator before. They're not allowed. They don't exist. This is undefined. Basically, this slope has all rise but no run, whereas a horizontal line has no rise but all run. It's an undefined slope. So basically, a vertical line is going to have the equation of x equaling a number, and the slope of a vertical line is defined as being undefined. So that's the difference between the two. Now these two special cases, although b is not a function, part A was, because basically this is like saying I could say that this is, even in slope-intercept form, I could say it's y equals 0x plus 2. So it is in slope-intercept form. It's also in a function form. This is a function. It passes the vertical line test, where obviously x equals -3, being a vertical line. Vertical lines don't pass the vertical line test. Sounds kind of weird, but remember, it's a vertical line test for functions. It's not a vertical line test for being a vertical line. Since these are functions we've been dealing with, even it's written in slope-intercept form, we could use functions for various reasons and applications. So let's have a look at a couple of them that you were presented to do, in the last couple of examples. Housing prices in a particular neighborhood increased at a rate of $3,500 per year. If you bought a home in 1980 for $65,000, assuming linear growth, what would it be worth today? Let H be the price of the house and let T be the number of years since 1980. So there's a number of things going on here. First of all, they're telling us that, we're going to have H being some function of T, where H is the price of the house, so it's the Y value, and T is being the number of years since 1980. They don't have to be X's and Y's. There's two things that they are telling us. They're telling us it increased at a rate of $3,500 per year. Well, one of the things that we have to appreciate about a slope, it's a rate of change. Now, usually we say it's a rate of change in terms of y in terms of x. It's an increase of y per increase of x. Well, it could be an increase of dollars per year, where, y is the dollars, x is the year. Or in this case, h is the dollars and t is the year. So basically, the rate of change is 3,500. In 1980, well, I'm not going to say T equals that. In 1980, H equaled $65,000. So it wants you to let T be the number of years since 1980. So if we're in 1980, the number of years past 1980 means that T equals 0. So when T equals 0, H equals 65,000. So it's basically telling us we have an ordered pair of 0, 65,000 as our ordered pair. This would be basically my Y, or in this case my H intercept. So basically, the formula I'm looking for is 3,500 T. This would be the B value, 65,000. Since it is a linear growth that we're assuming here, it could be represented in slope-intercept form. And so now, since I am recording this in 2019, I'm going to say today is, 2019. Since it's a number of years past 1980, T would be 39 years. So for me to figure out the price of the house today, I want to figure out what H of 39 is, which is going to be 3,500 times 39 plus 65,000. And if I work that out, 3,500 times 39 plus 65,000 comes out to be $201,500. Obviously, if you're watching this video, if it's a different year, then this would be off slightly. But that's how you would go by figuring out. You should at least be able to get to this far. The rest of it would depend upon what you interpret T to be based off of whatever year it is you're watching this video. So I hope we don't have to remake this from year to year. So, and the last example you were given, at the 1960 Olympics, Wilma Rudolph ran the 100-meter run in 11 seconds. In 1988, Florence Griffith Joyner, FloJo, set the Olympic record for the 100-meter run at 10.54 seconds. If the decrease in the time continues at this rate, which should the winning time for the 100-meter run be at the 2004 Olympics? And then they say the actual winning time in 2004 was 10.93. How far was the model off? So it's asking you two questions. We want to first figure out a model, calculate what it would predict for 2004, and see how close it was. So there's a couple ways to interpret this. One of the ways, as we saw before, is that, it was letting our X value or our T value in that case be the number of years since a certain year, and use that as, they kind of zeroed it out. That makes the numbers smaller to work with, but I can actually work with the actual years here. Just so you know, the 100-meter run part, the 100 that's in there, doesn't mean anything. I will see students try to put 100 into this thinking that it means something. It really doesn't. That's the event, but we're looking at the date versus the time it's run. And so the points I'm given that I know would be on a linear function, if I was assuming it was, is that I would have the year 1960, 11 for the number of seconds, and then I would have 1988, comma, 10.54. Now I could have adjusted this by doing this, but this makes it a little easier for me having to do more mental math and figure, okay, well, if 1960 was 0, what's 2004 going to be, and whatever the case may be. So I want to use this to come up with an equation where y equals the time the events run in, and x equals the year. You can make your own variations to this, by all means, but this is how I'm going to go about calculating it. So my slope is going to be 11 minus 10.54 over Since I took the 11 first, I'm going to take its x-coordinate first on the bottom, 1960 minus 1988. And it's okay for me to have a decimal as my slope, especially since I have decimals involved with this. So let me do the calculation real quick. And it comes out to be negative 0.01648, well, 29. That's enough decimal places. I'm going to still use all the decimal places that are on my calculator because it does have memory features on it. So when I carry through the calculator, I might report one number, but actually be using another number. So right now I have the formula y equals negative 0.016429 x plus b. I got to figure out what b is. And the way I'm going to figure out what b is I'm going to go back and take one of these initial points. I'm just going to take the first one for the sake of argument. And I'm going to plug in the x and y values and calculate what b has to be as a result. So I'm going to have 11 equals negative 0.016429 times 1960 plus b. So I'm going to have 11 equaling negative 32.2 plus b, which means b is going to equal 43.2. So that means that my model for this is y equals negative 0.01649 x plus 43.2. Now I have a formula. Now I can predict what happens in 2004. So in 2004, and the way I set this up is I let x be 2004. If you accounted for 1960 being the first one and you let that become your x equals 0, please make sure you're consistent with that. So here I'm going to have y equals negative 0.016429 times 2004 plus 43.2, and I would get y equals, and again I would calculate, I would get 10.28 seconds. And so the model, if I was using those 2 points as the winning, it's predicting the winning time, it's actually off by about 0.65. The thing is, that's what we have to, we would expect that a little bit because in 1988 she set a record, okay, which means that that's something that doesn't happen very frequently. It's not a common time. It's not a common thing to happen. It doesn't happen every Olympics that someone breaks a record. Or at least not for any one event. It isn't like from year to year to year. For each Olympic year, every time there's Olympics, the record gets broken for any event. So the winning time in 1960 and the winning time in 2004 may not have been record breakers. As you can tell, they weren't. They were both, well over that 10.54 seconds that FloJo had. So I wouldn't expect this to be a good model using those as 2 points because FloJo's um, winning time was kind of an extraordinary circumstance. But that's the end of this video. If you have any further questions about anything from 1.3, please make sure to bring them up to me in class. Until next time, have a good day.